In Learning Zig, Session 4 will cover strings basics and some safety. Zig has both string literal values and string objects. String literal value is a pointer to null-terminated byte array similar to C, so primarily it's a pointer to constant list of U8 items reading up to null. Zig's string literals carry length data as part of type information. String objects are sliced to an arbitrary U8 list, so it contains length of list along with pointer and doesn't require null termination. Presumes the strings to be UTF-8 encoded. And since strings are a list, we can loop through its bytes one by one. We already have a function sample string written in root.zig. In it, std.print gets a string literal. Created a string with its inference of a U8 slice for hello. And a for loop iterating over the all four characters of hello. Trying to run it shows our ASCII for hello is wrong and says LOSV. So let's tweak the int values for hello to match ASCII of hello and rerun. Making output more readable. It gives a quick insight into C language's strings for people who might have forgotten or never came across. Core thing is Zig's string forms carrying length information, makes it safer to allow checks for out of bound. I'll just quickly add hello and hello.len to last std.print. And a quick test run. Now let's look into string object type. @type of function allows you to check type of any object in Zig. Looking closely at string literal gives a constant pointer to a null-terminated U8 array. For string object, we use a slice of constant U8 values. The string object itself could be a variable and point to different slices though, but of constant U8 values. Let's write a quick sample function similarly for the type of flow to run ourselves and check the results. I'll move the stdout const to global so we can use it in newer functions. We'll add an int array with inferenced length and a string object with constant U8 slice for hello. Now we'll print type of int array, address of int array, also for a string literal and the string object we created for similar literal. Let's run tests to see result for sample type of. Then comes the section for byte versus Unicode. Since Zig accepts strings as set of Unicode character, the U8 list wouldn't directly map each byte to a character. So, if 65 is Unicode point for capital alphabet A and fits in a byte, but also there is Latin character of capital letter A with stroke with Unicode point 570 that doesn't fit in a byte, and instead gets represented as C8BA to be stored in 2 bytes. This is important to know as when we loop through items of string, we loop through the individual bytes and not the characters. So, to iterated through characters and not plain bytes, we can use std Unicode UTF-8 view struct to create an iterator for Unicode points. Here we have an example, so let's write a similar code piece in our samples and run to check. First, I'll initialize the UTF-8 view into a new variable UTF-str. Then instantiate the iterator into a new variable. Now let's use while loop with condition that next UTF-8 code point slice is available. Here we'll simply print out the hexadecimal code point for verification with help of std format library. Since our local variable isn't ever changing, compiler wants us to designate it constant. Running this shows us 3 hex codes per Japanese character. Time to take a look into useful functions for string operations. Zig has the important ones as other modern languages. The important ones listed here from std-mem library. To check string equality, split into substrings given a delimiter, split given a substring delimiter, check if a string starts or ends with a substring, trim specific values from both sides of a string, concat strings, count substring occurrence and replace a substring with another. Lastly, a quick look into section on Zig safety. In short, it starts with saying attack vectors gets multiplied by the number of layers involved in a particular logic block's execution. Constructs at hardware, kernel, programming language, libraries, external integrations, and more. then quickly mentions primary choices by ZIG to safeguard against memory attacks. Defer and defer for a readable deallocation of resources at an easy-to-not-miss place in code. There are testing allocators to detect memory leaks and double freeze, allowing unit tests to cover safety concerns. Collections to have their length embedded in object itself, making out-of-bound checks easier. Also, pointers and objects are non-nullable by default. Switch statements have to cover all cases. The compiler forces to handle most known problems during build itself. This is it for this session.